This is part 1 of lesson 10.7, Taylor Polynomials and Approximations. In this lesson, we are going to talk about what a Taylor polynomial is and a special case, which is called a Maclaurin polynomial. And we're going to talk a little bit, we're going to introduce the idea of approximation and error boundness, and we'll pick up on that later. So a Taylor polynomial is a polynomial of a certain type, and we've already worked with them a little bit. This formula right here, f of x is approximately equal to f of a plus f prime of a times x minus a, which was our linear approximation for a curve when we were trying to find a value. So that's actually a very simple Taylor polynomial of degree 1. What Taylor polynomials are great for is taking very complicated functions and writing them as a polynomial, because polynomials have such nice, well-defined properties that it makes it easier to work with. So that's where the idea of a Taylor polynomial came from. Now, one thing about this is you are going to have to know this formula, and it's not that hard to remember. So what you have is you approximate a Taylor polynomial with the notation p sub n of x, and it's equal to the value of the function at a specific area, and then the first derivative times x minus c, then the second derivative at that point over 2 factorial times x minus c squared, and then so on and so forth till the nth derivative over n factorial times x minus c to the nth power. So the thing to notice is if you get this part correct, these match up. The derivative you're on, the factorial, and the power to the x minus c. Now the thing you have to be careful with is you have to make sure it has n derivatives, so as many derivatives as you want. So there is a special case of that, and that's if it is centered at 0. Then it's considered a Maclaurin polynomial, and you'll notice the only difference here is now we don't have the x minus c part because c is 0. We just have x to the power, but they still match up. The derivative you're on, the power of the x, and this of course would have a 1 factorial over it. So they do still match up, the derivative, the factorial, and the power. So let's do a few examples with these. So example 1, suppose that f is a function which has continuous derivatives, and that f of 2 equals 1, f prime of 2 equals negative 3, f double prime, that should not be there. Let's just white that out there. There should not be a semicolon there. F double prime of 2 equals 5, and f triple prime of 2 equals negative 5. So we're to write the Taylor polynomial of degree 3 centered at c equals 2. So this polynomial, so our f of x is going to be our Taylor polynomial at 3. So it's going to be f of 2, which is 1, plus f prime of 2, which is negative 3, times x minus 2, plus f double prime of 3 over 2 factorial times x minus 2 squared, plus f triple prime of 3 over 3 factorial times x minus 2 cubed. And when you simplify this, you get p sub 3 is going to equal 1 minus 3 times x minus 2. And I'm just going to leave it like this so you can see the form for the first equation. I'm just going to get rid of that plus minus stuff. So that's the general form. For the next one then, we'll actually write it out. Okay, so one of the biggest things that Taylor polynomials is used for is to write some very important, very useful transcendental functions as polynomials. It makes them a lot easier to deal with, and we're going to look at those. And the three that we will look at are sine, cosine, and our e function. So they in themselves have their own limitations, difficulties, special cases, but if you write it as a polynomial, all those things go away and you can look at it in more general terms. So we're going to start with sine. We are going to start with assuming it's going to be a Maclaurin polynomial, which means we're going to center it at 0, and we want to write a degree 5 for it. So in this case, what we have to do first is we have to find the value of our 5 derivatives at x equals 0. So that's the first thing we have to do. So I'm just going to go ahead and find 5 derivatives. So f prime of x is going to be cosine x. F double prime of x is going to be minus sine x. F triple prime of x is going to be minus cosine x. The fourth derivative of x is going to be sine x. And then finally, the fifth derivative of x is going to be cosine x. And so then, from there, f prime of 0 is going to equal, when we put 0 in, we get 1. F double prime of 0 is going to be 0. F triple prime of 0 will be negative 1. The fourth derivative at 0 will be 0 again. And then the fifth derivative at 0 will be positive 1. So this polynomial is going to look like this. So we have f of x is going to be approximately equal to our Maclaurin polynomial of 5th degree. So I have the very first term. So if I put 0 in the function, because I need f of 0, I get 0, so I don't have that term. Then I'm going to have f prime of 0, which is 1, times x, minus, the next term will be 0, and then I have a minus. Then I'm going to have x to the 3rd power. You know what, let me write those in. Let me just write everything in first. I don't want to confuse anyone. So the very first term is 0. And then the first derivative is going to be 1 times x to the 1st. Then the next one would be plus 0 x squared over 2 factorial. Then the next one is going to be negative 1 over 3 factorial times x to the 3rd plus 0 over 4 factorial times x to the 4th. And then finally, we're going to have plus 1 over 5 factorial x to the 5th. So simplifying that then, our Taylor polynomial becomes x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial. So if you see here, the even powers, even the 0, they disappear. So I can actually write a general term here if I wanted to, and we're going to talk more about that in a little bit. If you see, I have an alternating series here. So it's going to be a negative 1, and it happens on odd powers. So I'm going to make sure that whenever n is negative, that's when this is going to happen. And then I'm going to have x to the 2n plus 1 over 2n plus 1 factorial, because 2n plus 1 represents odd numbers. Now you want to be careful. Don't get confused here. I know I just have an n here, But you're going to see when we write this in general, we're going to start our n, we're going to start our n at 0 and not at 1, so it'll work out fine. Okay, for the next one now, let's do cosine the same way we did sine, and we're going to see that the opposite's going to happen for cosine. We're going to get all the even terms of the Maclaurin polynomial. So let's just take our derivatives like we did in the other one. So we had f prime of x is going to be negative sine x. Then f double prime of x will be negative cosine x. F triple prime of x will be sine x. The fourth derivative of x will be cosine x. And then finally the fifth derivative of x will be negative sine x. And I know it says the nth derivative, and we're just going to do what we did before. Let's write one more term just so we have one more. If I don't write this one, I'm going to have more derivatives that are 0 than I will have non-zero. So just so we can see another term. So the sixth derivative then will be minus cosine x. So again, finding those values, f prime of 0 is going to be 0. F double prime of 0 will be negative 1. F triple prime of 0 will be 0 again. And if, like I said, they're going to alternate 0 and either 1 or negative 1. Okay, so of course our f of 0 here will equal 1. So our Maclaurin polynomial will look like this. So we do have a first term. There's our f of c, our f of 0 is 1. And then our first derivative will be 0. Our second one is going to be minus 1 over 2 factorial. And then we're going to have x squared. And then the next term will be 0. Then the fourth term is positive 1 plus, I'll just put it in the top, x to the cube, x to the third over 3 factorial. And then the fifth derivative is 0, and then I'm at the sixth derivative, which is negative, minus x to this, whoops, I am so sorry. Okay, and then our Maclaurin polynomial will look like this. We have our x of 0, which is 1, and then our first term is 0. Then the second term will be minus, and we have 1 x squared over 2 factorial. And then our third term is 0, and then our fourth term will be 1 x to the fourth over 4 factorial. Our fifth term is 0, and then our sixth term will be a minus again, x to the 6 over 6 factorial. And now in this case, we want our nth term, so I'll write it down here then, plus, and again, it's alternating, so we're going to have our negative 1 to the n, and now we're going to have x. Now we want even power, so we write an even number as 2n over 2n factorial. And again, we're going to start our n's, I keep pressing that one, we're going to start our n's at 0 instead of 1, so the signs will work out fine. So in example 4, now we want to do e. And the thing about e is all the derivatives will be the same. So I'm not going to write them out because we know that the nth derivative for all of these is going to be e to the x. It doesn't matter which power. So then if I do evaluate any of those derivatives at 0, I get e to the 0, which is 1. So every derivative is 1, and even the value of the first term here is going to equal 1. So I can just go ahead and write out the function and then figure out the nth term. So we're going to have 1 plus x plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and so on. So this one is the simplest of these three transcendental functions. Then we have x to the n over n factorial. So if you've ever looked up a way to express e to the x, here's where it comes from. You might have seen this online or somewhere. That formula there is the Maclaurin or Taylor polynomial for e to the x. Now, it is expected that you know those general formulas. Now, they might ask you to write it, or they might use it in some way. They might tell you to use like the Maclaurin or Taylor polynomial for sine of x centered at 0 to evaluate a derivative, figure out the behavior of the function, something along those lines. So let's go ahead here and write out the three in general form as a series so that you can see them. And this is going to serve us later because we are going to talk about Taylor series in a later section. So sine of x, and this will get back to what I was saying before about starting our index at 0, is equal to the summation of n equals 0 to infinity of our nth term that we found, which is negative 1 to the n x. Now remember, we want the odd terms, so that'll be 2n plus 1 over 2n plus 1 factorial. And if you start counting here, what you're going to see is the first term will be negative 1 to the 0 times x to the first over 1 factorial, because you'll have 2 times 0, and that will give us our positive x that we had. So that'll give us the first term that we had here, the positive x. So that's why it does work out good, especially starting the index at 0. So what we do want to remember from this is that this alternates on odd numbers only. We don't have any even powers. Now cosine is going to be almost the same thing, except that we have to have even powers. So we're still going to keep the negative 1 to the n, but now x is going to be to the 2n power, and we're going to have 2n factorial in the denominator because this is going to alternate on the even powers. So sine gives us the odd powers in a Taylor polynomial, and cosine gives us the even. And then we have e, and that one is pretty simple. We have no alternating series here. We just have x to the n over n factorial. All right, so I'm going to end this video here, and in the second part, I'm going to do some examples of working with some error that comes up sometimes, because of course these are approximations and not exact values for functions, and how we work with that.